This is the third lecture of Professor Kifer. So he continues his lectures on introduction of the transfer-parallel application. Please.
Thank you very much. So let me remind you that we started studying Kifer theorem. I will first recall what it is about. So we have a compact metric space X. We have the space calligraphic X, which is the space of measures, probability measures of X. So I always consider both sigma algebra. And we have a sequence UN. These are random variables with range in X. So these are X valued random variables. And the question is, when this sequence of random variables in N satisfies the large deviation principle. So we introduced two hypotheses. So we assume that there is a prefixed dense vector space V. Now, X is a compact set, C is the space of continuous functions. Of course, let's consider the maximum norm of the space of continuous functions. And we introduce the following two hypotheses. The first one, existence of pressure. It says that for any V in this weak-hand graphic, the following quantities are defined. Is the limit as n goes to infinity, 1 over n, logarithm, mean value exponential. Then I have n b un. We assume that this limit exists for any v in the weak-hand graphic. Now, in fact, we also prove that Q, so it is a function from Cx into R, it is one Lipschitz and convex. So particularly the fact that this one Lipschitz allows you, and V is dense, initially it is defined on V, it is not defined on CNX. Initially, it is defined on V, because V is dense and the function is one Lipschitz, you can extend that function to the whole space C of X. So Q can be extended to C of X continuously. And in fact, it's not difficult to see that this limit will exist for any V in C of X. As soon as it exists on a dense subspace, it will exist for any V in C of X. And the result will be, again, one Lipschitz and convex function. Then we introduced the Legendre transform of Q. So I of U, it is defined for all probability measures. I define it for sorry, I think I need to put this right. I'm sorry. Okay, now it's better. So we then transform I of U, which is the supremum when V is in C of X, V mu minus Q of V. Then the result of convex analysis shows that you can recover this function Q of V from I of mu by exactly the same formula. So one can prove that Q of V is equal to the supremum when mu is in Q of X V mu minus I of mu. And then we do the definition. Definition mu is an equilibrium state for V. By definition, we see that this equilibrium is saturated. In other words, Q of V is equal to V mu minus I of mu. And the second condition in Kifer theorem is that there is uniqueness of an equilibrium state for any V in this V category. For any V in V, there is a unique equilibrium state. So in fact, the equilibrium state in this setting always exists because of compactness and rho, so we can give the phi of mu. So the condition is that this equilibrium state should be unique. So there are two hypotheses in Kifer theorem: existence of pressure and uniqueness of equilibrium state. Then the results are the following. Theorem: if PP and UES are satisfied, then you have LVP. Then the LVP holds for mu n with the range function I defined as a Lagrange transform V or Q. And I also gave some ideas of the proof. I will remind you the idea of the proof. So we established that the LVP for mu n will be proven if we establish the following property. Following property P. There is a rate function I from x to 0 plus infinity, such that if nk is a subsequence and array function j again from x to 0 plus infinity satisfy LVP along the subsequence. In other words, we have this limit k goes to infinity 1 over nk. Well, this should be true for any gamma in Borel sigma algebra over x. Logarithm probability that mu nk belongs to gamma is equal with the, I think I introduced this notation, right? Which means that we have a large deviation up and lower gamma equal to minus I of gamma minus j of gamma. There is a rate function I such that if a subsequence nk, subsequence of integer positive integers nk, and rate function j satisfy this relation, in other words, large deviation holds for mu nk along the subsequence, then necessarily Vj is equal to this function I, which is independent of the sequence. So if you have this property, then you have LVP for the sequence mu n, for the whole sequence mu n. Now the idea is the following. So let's fix any n k and the corresponding range function j for which this is true. Right, so it gives numbers 1, 2, and 3. So suppose that n, k, and j are such that 3 poles. Then let us fix any finite subset gamma of this space B. Let us denote it by B1, Bn, B1, Bd. And let's consider now phi gamma, which goes from X to Rd and takes X into space of measure to take the measure mu to B1 mu. This is the integral of Bn with respect to mu, B mu. Right, so for each finite subset gamma, I can define the number phi gamma, which goes from the space of probability measures, from this set of probability measures into Rd, and defined by this formula. This time is continuous. Therefore, phi gamma applied to this mu and k satisfies LDP with the range function j gamma. How I define the j gamma? This is the very first result we saw, the fraction principle. J gamma of R will be just j, the range function governing the LDP for this one, calculated on phi gamma minus 1 of R. Right, so according to the fraction principle, this phi gamma and mu k satisfies LDP this range function. Well, suppose now that we can prove that phi gamma mu n satisfies LDP with some range function I. For instance, phi gamma mu n, for the phi gamma mu n satisfies the hypothesis of Gardner-Ellis theorem. Then the subsequence of this sequence will also satisfy LDP, and by the uniqueness of range function, the range function for this one must be the same as the range function for this one. So by the uniqueness of range function, we must have the following: is j gamma of R should be equal to the range function of this one. Let's denote that range function by I gamma. This should be true for any R in Rd. Suppose that for any finite set gamma, and for any finite set gamma, they have proved that this satisfies the large deviation principle, satisfies Gardner-Ellis theorem, and therefore the large deviation principle. By uniqueness, we must have this equality for any R and for any gamma. Now, but let us recall that this I gamma can be written according to Gardner-Ellis theorem, can be written as a general transform of the corresponding pressure. So I gamma of R is the supremum when alpha is in Rb of R alpha minus Q gamma of alpha. Which means that, so these two relations implies that this j gamma, which can be written as this, j of phi gamma minus 1 of R, is equal to this supremum alpha in Rb, R alpha minus Q gamma alpha. And this should be true for any R for any R, for any gamma and for any R. For any finite gamma and for any R in RT. The idea is that if we can prove this relation for sufficiently large family of functions gamma, subset gamma, because this right hand side, there is no sequence in Nk anymore. So this is independent of Nk. And if there are sufficient in any families for this to be true, then I may hope that this will determine uniquely this function J. Because these are some subsets of the space, so this is subset in T of X. T of X. In my space, X got. So if I know the minimum of my function of sufficient in any subset, then I may hope to recover it uniquely from this relation. Once I have uniqueness, I can apply this this property that this T implies derivation. So now this is a general idea, and in fact the proof is not that complicated. The proof is based on the following result, which I call Dawes and Gardner-Puhansky theorem. Now, before formulating it, let me call you the concept of partial order. So now it is completely abstract result. There is no any assumption of this type that this is this gamma is the finite set in V and so on. So I fix compact metric space X. I fix mu n, which is a sequence of X valued random variables. And I fix a set G with a partial order. So what is a partial order? Partial order is a relation of G. Now, if you want to be concrete, then think of G to be the set of finite subset of V. So in application, this G will be finite subsets of V, but the result is completely abstract. And this partial order is just the order of inclusion. So what is the partial order? Partial order is a relation of the set G. It satisfies the following three properties. For any gamma in G, gamma is smaller than gamma. The second property, for any gamma 1, gamma 2 in G, if gamma 1 is smaller than gamma 2, and gamma 2 is smaller than gamma 1, then necessarily these two are equal. Finally, if you have three elements, gamma 1, gamma 2, gamma 3 in G, if gamma 1 is smaller than gamma 2, and gamma 2 is smaller than gamma 3, then gamma 1 is smaller than gamma 3. In addition to this, we will assume that for any finite set, there is an element which is larger. In fact, it's quite a solution for only two elements. So I will assume in addition that for any gamma 1, gamma 2 in G, there is gamma such that gamma 1 is smaller than gamma and gamma 2 is smaller than gamma. Obviously, all these relations are satisfied for this set for the finite subset of V. Right? You have inclusion relation of that finite subset. So these properties are obvious, as in the last one, because we have two sets which are taking union, again for the finite subset, and it is larger than the two others. Now, here is the theorem. So suppose we are given this space X, the sequence mu n. So in addition, we have X gamma, family of Polish spaces. Oh, we can even assume that this is a path space. And phi gamma being continuous maps such that you have the following two properties. The first one is monotonicity. What I mean by it, I mean that if gamma 1 is smaller than gamma 2, then okay, let's write completely phi gamma 1 minus 1 phi gamma 1 mu. So I'm taking to measure mu. Oh, sorry, it's not measure, it's just x. We measure later. Phi gamma 1 x, and then taking the inverse image. So this is set which is much bigger than x. So gamma 1 is smaller than gamma 2. This one is larger. So this is a decreasing family. Okay, so for each gamma in this partially ordered set, I have a map phi gamma. I take any element x, so this is true for any x. For any x in x, I must have this. I take phi gamma 1x, I have an element in x gamma, and I take the inverse image of this element, which will be much bigger than x. Then I do the same with gamma 2, which is larger than gamma 1. What I get should be smaller. And if you think of this example, this is trivially satisfied. And in addition, I assume that, again, for any x, if I take the intersection of all of them, then I will get single from x. All these sets will contain x, right? Because by definition, I take phi gamma of x, and then so let's the picture. So in this space x, I have an element here. I consider phi gamma x. So this is an element in x gamma. And I consider the inverse image of that. This will be whole subset there. This is phi gamma minus 1 of phi gamma x. So in that follow, let me denote this by k gamma x, not to write each time the two phi gammas. Right, so I take x, I take phi gamma x, this is element in x gamma, and then I take the inverse image. This is a huge, well, this is the set which may be larger than x, but it always will be there. X is always here. Now I take the intersection of all of them, I must have only one element in the intersection. And this is precisely what I was saying here. That if I have sufficiently many relations of this form, then I will be able to conclude that J is unique. So this is precisely the condition guaranteeing that there are sufficient many. Okay? And then the second condition is L with P gamma. L with P beginning gamma, emphasize that it is not L with P for new n for the image. So for any gamma in G, if I take phi gamma mu n, so this is a x gamma value sequence, so this satisfies LVP with rate function, which I denote by I gamma. So these are the hypotheses. I have a sequence of x value random variables. I have a big family of Polish spaces. And I have continuous maps for which we have monotonicity and LDP for the image. Then UN satisfies LDP with the rate function, which can be written explicitly. I of x is equal to the supremum when gamma is in G of I gamma, this rate function, applied to phi gamma of x. Okay, so this is the Dawson-Gardner-Pochacki theorem. But Dawson-Gardner was a more general result. And Pochacki conclusion is that when you have this additional condition of compactness, which is certainly true here because our space is compact, then the result is much nicer and much easier to verify with a simple proof. So I will prove this result. Okay, proof. Well, let's see what we want to prove. We want to check that condition, right? We want to check condition P in this more general setting. We want to prove that if you have a subsequence which satisfies LDP, then the corresponding rate function does not depend on the subsequence. So let us take the subsequence NP and let us find the corresponding rate function J so that U and K satisfy that relation free. Then the argument that I give there shows that J gamma of, well, I'm just copying the formula. There was that J gamma, no, it's not J gamma, it's J of phi gamma minus 1 of R is equal to what? Is equal to I gamma of R, and this is true for any gamma in G and for any R in for any R in S gamma. Right? Right? Because I have this exactly the same argument is here. Right? I consider the image, I consider the full sequence, the rate function for this one. Now I don't need that is precise form of this general transform, it is just I gamma. And I can put the rate function of the contracted sequence is the same as rate function I gamma. So now I need a lemma. So in particular, I can write that for any x in x, J phi gamma minus 1 phi gamma x is equal to I gamma phi gamma x. Because I just took R equal to phi gamma x. I didn't change anything. This is true for any R in x gamma, in particular, it is true for phi gamma of x. Now, a small lemma which says that if J is lower semi-continuous, again, there is no special function, just any lower semi-continuous function on a space X. And K gamma is a decreasing sequence is a decreasing family, then if I calculate J on the intersection, then it will be the same as the supremum when gamma is in J of K gamma. Okay, I have a lower semi-continuous function and a family of decreasing subsets. Sorry, I need then the family of decreasing family of closed subsets. They need to be closed. So then, in this case, it will be also compact, or compact. We can write compact subsets. Then you have this. Okay, so you have for X, you have this one, and you have also this. Now let's apply this formula to J in K gamma equal to K gamma X. So I take K gamma X. Let me remind you that this is phi gamma minus 1 of phi gamma X. And let me write this relation. So I have J on the intersection of K gamma X. But what is the intersection of K gamma X? By hypothesis, it is just the space, the singleton X. So I have that this is J of X on one hand. On the other hand, it is the supremum of when gamma is in G of J of K gamma of X. But what is J K gamma of X is exactly this. So this is I gamma of phi gamma of X. So I started with J of X, which was the rate function governing large deviation principle for the subsequence mu and K. I ended up in this formula, which is completely independent of the subsequence. And this completes the proof. Okay, so this important results are repeated once again what we did. So we have a sequence of X valued random variables. We fix a family X gamma, Polish spaces and continuous maps, such that these two conditions are satisfied: monotonicity, and they are sufficiently many in the sense that if I take the intersection of this set, I get X. And second condition is that for any gamma, the image of the sequence mu n satisfies the LDP with a rate function I gamma. Then the conclusion is that the full sequence mu n satisfies LDP, and you can write explicitly the rate function. I will probably skip for the moment the proof of this lemma. It is really nothing complicated. It's just compactness plus laws of continuity. Right, so maybe to get some intuition, you can try first. Let me leave it as it is. Try first to prove when K n is a sequence. In this case, it will be easier. It's just decreasing sequence. Then you can use sequences. In the general case, you just need to use compactness of the intersection, power it with some goals, so that the infimum over the goal is not too much smaller than the infimum than the value at the center of the goal. Subtract the spine subcovering and get the result. Okay. In one direction, the result is obvious. In the other direction, you need to use compactness of semi-intermediate. So this is the Dawson-Gartner-Puchalski theorem. Now we are ready to prove Kifer's theorem. Well, the idea is to apply this BGP theorem. So the proof I will divide it into two steps. Step one, application of Dawson-Gartner-Puchalski theorem. So the topic is already described there, what we are doing. Right, so what we need to do? We need to check those two conditions, monotonicity and LDP. Well, for monotonicity, there is almost nothing to do. Because what is our G? Our G is the finite subset V1 VD, right? Then our map phi, so I will denote this by gamma. Our map phi gamma of nine measures mu will be V1 mu VD mu. What is K gamma of mu? K gamma of mu is the inverse of phi gamma mu. So this means that we have all measures of X such that Vi mu is equal to Vi mu is equal to Vi mu. This should be true for I between 1 and V. So here mu is fixed, mu is the measure which varies. So I consider all those measures for which the mean value of the functions Vi is the same with respect to mu and with respect to mu. Obviously, if I take more conditions, I will have smaller subsets. So monotonicity is obvious. Gamma 1 is included. Gamma 2 implies that K gamma 1 of mu is greater than K gamma 2 of mu. So gamma 2 imposes more conditions. And what about the intersection? The intersection, we can say that this is the space of all measures such that I can take any finite set. I can say that I take particular fingerprints. So this means that y v mu is equal to v mu, and this is true for any v in v graph. So I have a dense subspace on which the two measures mu and mu are the same, and therefore this is singleton mu. So the monotonicity is proven. Now we need to check the LDP. LDP for the contracted, for the contracted, right? So for this, we apply Gartner-Puchalski theorem. What are the conditions of Gartner-Puchalski theorem? They are more or less the same as in Kifer's theorem. The distance of pressure and differentiability, which in this case is formulated as the index of equilibrium state. So let's begin with the existence of pressure. Q gamma alpha. We have not calculated this already. Let's do the calculation. So this is by definition the limit as n goes to infinity, 1 over n logarithm. Mean value. Now we have exponential n. So now we are living in the space Rd. right? Because our map phi gamma is a map from Px to Rb. So I didn't write it, but this map phi gamma take Px, which is our space x graphic, to Rb. Now I need to write the inner product in Rb, you fill in the product already, of what? Of alpha and phi gamma un. But what is written here, with the calculating that, alpha phi gamma un is the inner product of vector alpha 1 alpha b, b1 un, b un. Right, so we have two vectors, and I'm taking the inner product. So here, this bracket are the integral. This one is the inner product in Rd. I need to take component wise, right? The sum j from 1 to b, alpha j, bj, un. And because everything is linear, I get b alpha integrated with respect to un. So where is the alpha? Who is the alpha? The alpha is alpha 1 b1 plus alpha n alpha b bd. And so this expression in the exponent can be written as follows. The limit as n goes to infinity, 1 over n logarithm mean value exponential n, and I have here b alpha integrated with respect to n. So this limit exists according to my first hypothesis EP. So that limit exists for any function b which is in beta graphic, and because I took functions in beta graphic, it is a vector space, therefore linear combination is again in beta graphic. So this is exactly what I call QB alpha. So the pressure exists. So what we need to do now is to see why this function is differentiable. Once I prove that this function Q gamma alpha is differentiable, I can conclude that the LDP holds, and also I need to find the right function I, which can be calculated by this formula, the formula given by the Dawson-Gardner-Tokarski theorem. Okay, so we need to check differentiability of Q gamma alpha. This is the second step. Now let's see what we have. We have the function Q of B. And so this is the function which is defined on first on the graphic, and then we can extend it to the whole space C of S. The associated with this function is the linear transform I of nu. On the other hand, taking here b equal to the alpha, we have constructed Q gamma alpha, which is nothing else but Q of the alpha. And we have associated with this one the linear transform E gamma of R, Q gamma alpha. Question is, what is the relation between this I of nu and I gamma of R? My claim is that this is exactly the construction of this function I of nu given in the theorem in the contraction principle. So claim I gamma of R is equal to the infimum of I nu such that P gamma mu is equal to R, or in other words, it is I phi gamma minus 1 of R. Okay, so why is it true? Let's find the definition of I gamma. No, sorry. We'll do differently. Well, these two functions are, this function is convex, this one is convex. If I prove that they will generally transform the same, then I will be done. When I generally transform this one, is this 2 gamma alpha. I need to calculate the general transform this one, and they multiply. So when they know this function by g of r, and let's know this the general transform by g star of r, g star of alpha. Okay, so who is g star of alpha? G star of alpha, by definition, is the supremum when r is in Rd, alpha r minus g of r. Right, so this is the definition of the general transform. Now I use the definition of g of r. So this is the supremum when alpha is in Rd, alpha r minus g of r. It is the infimum of what? Of I of mu when p gamma of mu is equal to r. Right? Now I put this infimum in front of everybody. So I have an infimum with a sign minus, it becomes supremum, and I have here r, which is the same as p gamma mu. So I can write this as supremum alpha in Rd and p gamma mu equal to r. Then I have here, sorry, this supremum is equal to r. R. Okay, with r. Start with r, it should be r. With r here by p gamma mu. What I get here is alpha pi gamma mu minus I of mu. But we know already that this alpha pi gamma mu, here is alpha pi gamma, this is mu n, so if mu n is mu, then we will need mu as well here. So this is the supremum, when r is in Rd, pi gamma mu is equal to r, and I have here b alpha integrated to mu minus I of mu. Now let us look at this this expression. I have all possible r's and all possible mu for which p gamma mu is equal to r. This basically order mu. Because r is arbitrary, therefore I can take any mu. This is the same as supremum mu p of x, b alpha mu minus I of mu. And this is, according to inversion formula, this is exactly q of the alpha, which is q gamma of alpha. So I have proven that the general transform of this convex function is the same as q gamma alpha. Therefore, I is equal to I gamma of r is equal to this one. Okay, I can imagine that the proof is in heavy, so let us see once again what we are doing. We are trying to prove Kifer's theorem. Kifer's theorem says that if you have existence of pressure and uniqueness of equilibrium state, then you have aggregation base. The result called Dawson-Gartner-Kopetsky theorem shows that it suffices to check two conditions: monotonicity and LDP for the image. The monotonicity follows immediately from the definition. We are now trying to see why gamma alpha is differentiable. The first step is in this diagram. I have a function q of v, which allows me to construct the general transform I of v, which is my candidate for the main function. I restrict it to the subspace spanned by functions entering gamma. So it is called q gamma alpha, or q alpha, which is denoted by q gamma alpha. And with this q gamma alpha is associated with its congenital transform. The question is, what is the relation between I of and I gamma of R? The answer is I gamma of R is the construction of I loop in the following set. I gamma of R is I calculated on the inverse image of R, and here is the proof. So this is attraction. And here you take restriction on subspace, here you have attraction. And now we are going to prove the differentiability. Okay. Is here. So we'll fix the point alpha. We discussed the property last time in the one-dimensional case. It says that q alpha, q is differentiable at alpha, at this point alpha, if and only if the equation let's write q gamma. The equation I gamma of R plus q gamma alpha minus R alpha equal to 0 as a unique solution R. Okay, so this is a property of the general transform. I gamma of R is equal to the supremum, q gamma of alpha, q gamma of alpha is the supremum of R alpha minus I gamma of R. The supremum with respect to all R. So this equality, this supremum is saturated on the subdifferential. So this is equal to R naught alpha minus R gamma R naught, if and only if R naught is in subdifferential of 2 gamma at the point alpha. So this is a property of convex functions, which is easy to see in the one-dimensional case. This equality is saturated on any direction, on any slope, which is below the graph. Okay, so it is really not difficult to understand. In the one-dimensional case, it's very clear. In the multi-dimensional case, with some more work, you can prove it. So let's begin the fact that for convex functions, the supremum, which gives you an expression for 2 gamma, is saturated if and only if R naught is a subdifferential of 2 gamma. Now, the fact that 2 gamma alpha is differentiable is equivalent to the fact that the subdifferential is a single. So 2 gamma is differentiable, 2 gamma is differentiable at alpha if and only if dq gamma alpha subdifferential of the point alpha. So in the multidimensional case, it means that all the planes which are below the graph. So d gamma subdifferential of the point alpha is a singleton. Okay, let's assume that q gamma is not differentiable as a point alpha. Then there are at least two vectors in the subdifferential. So if q gamma is not differentiable at alpha, then there are R1, R2 in the subdifferential of alpha. Now, on the other hand, I know that this R1, R2, well, which means that this relation has at least two solutions. This is the same as saying that I gamma Ri plus Q gamma alpha minus Ri alpha is equal to 0 for I equal to 1 and 2. Okay, so this is a key observation. It's called Reuel-Walker's argument. So Q gamma is not differentiable at alpha, implying that this equation has at least two solutions. Now, but we know that I gamma is the contraction of my function I. I gamma is the contraction of my function I. And we have seen already that well, we have seen the existence of equilibrium state. More or less the same compactness argument shows that there are vectors mu I in Px such that P gamma of mu I is equal to Ri and I gamma of Ri is equal to I of mu I. So when I'm saying that in this contraction formula, is equally saturated with some vectors, some measurement. So due to the fact that I is also the continuum, the space is compact, phi is continuous, just choosing minimizing sequence, you can easily show that the limit will saturate this infinite. So I can construct mu such that phi gamma mu is equal to R, and this I of mu is equal to I gamma. Now there are two vectors, I can construct two measures, mu1 and mu2. There are two measures, mu1, mu2, such that phi gamma mu I is equal to Ri, and you have equality here. But these R1 and R2 are different. Therefore, mu1 is different from mu2. I've constructed two different measures such that now I'm rewriting this equality. What it gives I of mu I, because I have this equality, minus plus Q gamma alpha is the same for both. This is Q of V alpha minus R minus, I'm writing again, phi gamma of mu I, inner product with alpha is equal to 0. And this means that if I take this to the right hand side and use again the fact that phi gamma mu I alpha is nothing else than V alpha integrated with respect to mu I, I get. I'm taking QV, I'm taking this to come to the other side. I obtain Q V alpha is equal, this term will be V alpha mu I and minus I of mu I. And mu1 is different from mu2. So what it showed that this V alpha has at least two different equilibrium states which contradict the fact that any being in the graph has a unique equilibrium state. Okay, just very mild convex analysis shows that if Q is not differentiable, well, now this might the idea is additive. So if Q is not differential at some point, then you will have two different equilibrium state force and vector, force and function v alpha, which is a contradiction. So what remains to show is the formula for the rate function. So we need to prove that the rate function is given by exactly this formula, but this is almost ready. Because those graphics here and those graphics capacity here gives you an expression for the rate function. The rate function is given by the supremum, so let us add this supremum. I of u is given by the supremum for gamma in G, and I need to take I gamma or phi gamma mu. But this I gamma phi gamma mu is already calculated somewhere here. Okay, so this was the English transform. So let's calculate once again. I gamma mu, the supremum when gamma is in G. I gamma mu is the English transform from Q gamma. I need to take supremum alpha gamma b, and then I have alpha phi gamma mu minus Q gamma alpha, which is Q of the alpha. Now, this is, we know already calculated, and this is the alpha mu. So, what we get is the supremum gamma in G and supremum alpha in RD. Here, V alpha mu minus Q of V alpha. So, in particular, if I take both supremum, if I take all the functions in V, and because V in V graphic, because V is dense, then this is obviously equal to supremum, and V is in C of X, V mu minus Q of V. And now the proof is complete. We have proven that there is variation principle, and we calculated the rate function using the formula given in those and Gardner theorem. And this completely. So I hope these ideas are clear. So we have 25 minutes approximately to see what will come now and next time. So this is all what I wanted to tell you about that theory. Now, yeah.
So this is restricted to the setting that you always have the convex rate function, right? This setup.
Indeed, indeed. Each time you apply the Dark-Lewis theorem, you automatically get convexity.
By the assumption of theorem.
Yeah, Dark-Lewis says that you need some regulation conditions. I call it regular conditions. When you have regular conditions, therefore you have dark relation to convex rate function. Okay, now let's discuss the application. Also, we are now part of the theorem, which is a generalization of Dark-Lewis, which applies to infinite dimensional sets. Right, so Dark-Lewis applies to finite dimensional. Second Kifer applies to infinite dimensional. Second Kifer, people can apply to the space of measures. Okay, so this is the third chapter. Non-scalar theory for Markov process. Obviously, I cannot give even an introduction to the Markov processes. So for those who are not familiar with the theory, you can think of finite state Markov processes. In that case, the theory is non-trivial, although you know the Kifer theory, but you can find out errors. So again, I will be working in a compact metric space. And I consider a Markov process which are denoted by xk dx. So this is Markov process. So what does it mean? It means that we are given the following object. We are given a measurable space, which are denoted by omega f. Yeah, so just for those of you who are lost in the proof of Kifer and so on, you can forget about the proof, you can just remember the theorem. What I'm going to tell here does not use anything from the proofs. We will use just the formulation of Kifer theorem. So when I measure the space, we have a process xk of omega. This is a x-valued random process. Okay, so we have one process, but we have many probabilities. And we have family of probabilities, Px. Family of probability measures. On X, it borrows in algebra. So what is the hypothesis? The hypothesis is that the Markov property is satisfied. What does it mean? It means the following. Maybe different ways of writing Markov process, but Markov property that we write in the language of initial probabilities. For any gamma is borrowed subset in X. For any integers n and k, we have the following relation, and for any x in x, we have the conditional probability for the process. Well, this x is the meaning of the initial point. Well, the process starts from this point. I think I forgot to mention that. Okay, so you need to have Px and 0 equal to x is equal to 1. Okay, and then we'll probably measure on x, such that if you consider your process x naught, then it starts from x, it will be 1 is equal to x, the initial point. And you have the Markov property x n plus k belongs to gamma, conditional probability that this belongs to gamma given the sigma algebra in f time n is equal to the probability of the process starting from y. I can take here x k, precisely with k in gamma, and I need to take y equal to xn, and this is true Px almost surely. Well, if you didn't see Markov processes before, then probably this is too abstract. What is important here is that we can construct an object associated with Markov process which forms a semiloop. For that, we introduce this phi fn in the sigma algebra generated by x naught xn. Now, well, this property is something natural, but it takes time to understand what it means exactly. What it implies is the Kolmogorov-Chapman relation. And it is about the transition function. Let's introduce what is called transition function. Defined as follows: it depends on two parameters, k, initial point x, and the set gamma. And it is the probability that the process starting from x at time 0 belongs to gamma at time k, exactly this quantity. Right, so this is the probability that process starting from x is in the set gamma at time k. So the Markov property says that if you look at your process at time n plus k, knowing what happens after time n, then it is the same as looking at your process starting from xn, which is now random, and looking what happens at time k. Anyway, so you have this, and one does Kolmogorov-Chapman relation, and in the following: k d, well, it is a consequence of Markov property, k plus n x gamma is equal to the integral over x en x dy dk y gamma. This is Kolmogorov-Chapman relation, and Kolmogorov-Chapman relation allows you to prove an important property for the associated signal. So this is a function which depends on x and on the set gamma. So I can use this function to define some operators. But before doing that, I will use an hypothesis. It's called Taylor property. I denote it by F. This Taylor property. It says that the function which takes x to the measure p1 x dot. So this is a function from x to the space of probability measures is continuous. And so you have a function which depends on k, x, and gamma. When k and x are fixed, you have a probability measure. So for each k and x, this is the probability measure. The Taylor property requires that the function we take x to this probability measure time 1 is continuous. Well, it is the same as saying that it's exactly the same property as saying that for any f which is continuous, well, the thing that they are really compacted to so continuous functions are also bounded. For any f continuous p1f defined as follows: p1f is at the point x is integral over x p1 x dy f of y, this is the definition, is continuous. Okay, so this is our setting. We are dealing with Markov processes in a discrete time Markov processes in a compact metric space. Well, important property of Markov processes is that the transition function satisfies the Kolmogorov-Chapman relation. We introduce Taylor property. We will always assume that this is true. And when this is true, you can define what are called Markov operators. Well, there are two operators which are dual. pk, which acts, in fact, this is an iteration of this. But let me write for the definition in the property. pk f of x is the integral over x pk x dy f of y. So this operator acts in the space of continuous functions. The fact that if you take continuous function, you obtain a continuous function with a constant of Feller property, and you have pk star, which acts in the space of probability measure. So I need to define the measure. So this integral over x, pk x gamma mu of dx. So pk star acts in the space of probability measures. And a simple exercise, which is based only on a work check and relation, is that these two families, pk, well, of course, P0 is identity by definition, pk star are semigroups. So this is the first part, and the second part, for any f continuous for any mu in Px, we have this draw relation. Pk, if I integrate pkf with respect to mu, it is the same as integrating f with respect to pk star mu. Okay, so this is our setting. We're working with discrete time Markov processes in a compact metric space. We want to see if large deviation property holds for empirical measures. Now, in the very first lecture, I introduced an example. Differential equation with manual coefficients. So we'll take trajectory of the differential equation, restrict it to integer times, and under some hypothesis on the randomness, you will have a Markov process. And for that example, I introduced what I call empirical measures. Now we don't need a particular form of those random variables. You can just deal with general Markov processes. So we have this sequence, we have this Markov process xk. I introduce un, which is 1 over n, the sum k from 1 to n, Dirac mass at the point xk. So this is the Dirac mass. So this is our delta y is a probability measure, and the delta y of gamma is equal to 1, and y is in gamma 0, and y is not in gamma. Delta x gamma is a measure on x, is a probability measure on x, but it is random. It depends on xk, which is a random process. When I take time variable, I again obtain a measure in px, which is random. So un is a px value random variable. Now, question. Does the sequence un considered on the px, because I have many points of x. I can consider the standard trajectory starting from any initial point x. So that is because un considered on the px satisfy large deviation cases. Question I want to start. We only want to study random measures, it's Kifer theorem. So Kifer theorem has two hypotheses. The first of them is the existence of equilibrium state. So let us try to see how to write this condition. Sorry, existence of pressure, not existence of pressure. Existence of pressure, I need to study the following function, following limit. Q of V is the limit as n goes to infinity, 1 over n, logarithm, mean value exponential, n, v integrated against un. But now un is not arbitrary, now un has this particular form. Let's try to understand what it is. If I write n, v nu n, what I get n, v, I replace un by its expression, 1 over n, the sum delta is k, k of n. So I can simplify by n, and I can put the sum in front of it, everything, the sum k from 1 to n, and what I get is v integrated with respect to delta is k. And this is exactly v in the point x k. So what I get here is the following. The limit n goes to infinity, 1 over n, logarithm, mean value exponential of v of x1 plus v of xn. Indeed, it's a direct. No, indirect, not in the sense of distribution, indirect in the sense of measures. Right, so yeah. We don't have distribution, just x in abstract measured space. So we have this delta is in the sense of measures. So now the next point is the following. Well, people who are significant with paying casting groups easily recognize these paying casting groups. So what it means that I introduce the following object. I write p d of n applied to the function f to the point x. X is the following: the mean value, the point x, exponential the sum v of xk, k from 1 to n, multiplied by f of xn. So if I introduce this object, then what is written here is the following: q of v is the limit as n goes to infinity, 1 over n, logarithm p and v applied to a function which is identically equal to 1 and calculated to the point x. And because I'm sorry, I want to study the sequence on the px, so I need to specify here the initial point. Okay? I need to specify the initial point because I have a lot of it. I need to specify the probability with which I'm studying this sequence. So I have ex here, so in principle, these two also depend on x. And there are situations when indeed these two depend on x. So qx is the limit of this operator. So this is a linear operator in space of continuous function. Now again, using the Markov property, one can prove the following simple lemma. Says that P and B is a continuous semigroup of continuous operators in C of x. So in particular, P and B is equal to P1 V power n, to the power n. Right, so you have a semigroup, and the main hypothesis in the Donsker-Varma theory is that this semigroup possesses a leading eigenvalue. And so let me formulate that hypothesis. So this is what I call regular situation. What does it mean? It means that you have the following. So regular situation, I mean that P1B is a leading eigenvalue. So what does it mean exactly? It means the following. Yeah, I need to specify who is B. And I do exactly what is required in Kifer theorem. There is a particular subspace for which something is true, and that, so I introduce dense subspace B. So there is a dense subspace B such that for any B in this Minkowski graphic, there is a positive number lambda B. There is a positive function HB, and there is probability measure mu B such that lambda B minus n P and B by F converges to F integrated with respect to mu B and multiplied by this function HB. So we have a function in sequence of function in Cx. This is the function in Cx. So I want this convergence to hold. So this is from as n goes to infinity, and the convergence should hold in Cx. So this is our main hypothesis, which is imposed on our Markov process. Okay, so we are dealing with Markov processes. We have, yeah, sorry. So that for any thank you. For any continuous function f, I have converted to limits. N goes to infinity. Just 1 second. Yeah, n goes to infinity. Well, we forgot to mention that this HB should be eigenfunction of P1, but maybe it follows, maybe it doesn't. Okay, so there is HB positive such that PV HB is equal to lambda with HB. That will follow from this one. That will certainly follow. From here, that it does not follow that this function doesn't have anyway. I require this is the function. And there is convergence. Of course, this convergence implies convergence also for P and star, but this is really the consequence of I don't actually use this condition. So Donsker-Varma theorem of aggregation is about the situation when this semigroup, I forgot to mention that it is called Feynman-Katz semigroup. Okay, so Feynman-Katz semigroup should be regular in the following sense, in that sense, that there is a leading eigenvalue in the sense that there is a vector, which is an eigenfunction, eigenvector is PV. So this is P1V. There is an eigenfunction of P1V, and everything else converted to this. So this is a really isolated eigenvalue, which describes the asymptotic behavior, large time behavior of this semicolon. What we are going to show next time is that as soon as we have this property, you can check both conditions in Kifer's theorem, existence of pressure and uniqueness of the relationship for exactly that subspace V, and therefore we will have our relation principle for the empirical measures. And in addition, now we have a concrete situation, we'll be able to find a bit more complete, again, as a variational formula, but still simple variational formula for the right function. I think I'll stop here and
Questions?
Just this eigenvalue is for the P1, right? For the
in the P1, yeah. P1 BHP is
and then it describes as a not behavior as n goes to infinity.
exactly, yeah. N goes to infinity.
This is the lambda n on
Lambda B to power minus n.
Is it small or large?
It can be both small and large. Because we have a function B which is arbitrary. If B is equal to 0, then it will be exactly 1. If B is greater than 0, essentially, then it will be greater than 1. If B is strictly smaller than 0, then it will be smaller than 1. Otherwise, it depends on the areas. So it can be both. It is certainly positive, but we cannot say in general what is the sign of the variable.
If it is smaller than one,
It's booked on sorry?
looks like it go up.
Yeah, then the P and D goes to 0. If number one, number V is smaller than 1, then number V to minus n is exponential growing sequence, which means that this P and D must decay sufficiently fast that the two sequences compensated give a positive value.
Thank you very much.